Hello and welcome to my science tutorials. In today's video, we want to look at a purely capacitive AC circuit. Before we begin, if you are new to my science tutorials, kindly consider subscribing and turning on the notification button so that you do not miss any of our latest tutorials on biology, chemistry, mathematics, and physics. So without further ado, let's begin today's tutorial. So when we talk about a purely capacitive AC circuit, that is a purely capacitive AC circuit, we are talking about a circuit that only has a capacitor as the main or the major component. So if we draw the circuit diagram for that, we are going to have our capacitor over here, then we're going to have it connected to an AC source. Okay, so the AC source is going to have a voltage that we are calling a capacitive voltage, and then the current flowing through this circuit is what we are calling the capacitive current. So this is our circuit diagram. And this is our capacitor over here, so we are going to represent that with C. And then we are saying our AC source, which provides the voltage, is what we are calling the capacitive voltage, and then the current flowing through this entire circuit is what we are calling the capacitive current. Now in a purely capacitive AC circuit, the current that we see over here leads the voltage by 90 degrees. What do we mean by this? It means if we draw the phasor diagram for this particular circuit, we are going to get something that looks like this. We're going to have our current over here, and then we're going to have our voltage on this axis over here. So the angle difference between the capacitive current and then the capacitive voltage is 90 degrees, as we can see over here. So this is what we mean by, in a capacitive AC circuit, the current is leading the voltage by an angle of 90 degrees. Now if that is the case, there should be a way for us to be able to find the opposition to the flow of current in this particular circuit. Now in this type of circuit that we are calling the capacitive AC circuit, the opposition to the flow of alternating current is what we call the capacitive reactance, which is denoted by XC. So we call this the capacitive reactance. Now this capacitive reactance XC is given mathematically as the ratio of capacitive voltage to the capacitive current, which means that if we try to make voltage the subject over here, voltage, capacitive voltage, we are going to have the product of capacitive current multiplied by XC, which is the capacitive reactance. Now this looks like something. This looks like the Ohm's law formula that we use for direct current, that is V is equal to IR. In this case, the voltage is what we are calling the capacitive voltage. The current I over here is what we are calling the capacitive current, and then the resistance of the resistor in a direct current is what, in this case, because this is an AC circuit and it only has a capacitor, that is what we are calling the capacitive reactance. So this is just Ohm's law rewritten in an AC format. So this is for AC circuit, and this is for direct current. Okay, now we said that the capacitive reactance is given as the ratio of the capacitive voltage to the capacitive current. We also know that in an AC circuit, we know that the current and then the voltage do not go in a straight line, they go in a wave-like pattern. So this formula can also be written in another way. So we have the first one being VC over IC, but this can also be written as 1 over 2 pi FC, where F is the frequency of the of the circuit. So we have the frequency. This is the frequency in hertz. And then we have C is the capacitance of the capacitor. The capacitance of the capacitor is measured in farad and sometimes microfarad mostly. So this is another way of writing the capacitive reactance of a capacitive AC circuit. So this is a very important formula that we're going to be using throughout our calculations involving capacitive AC circuit. So you may want to note that somewhere. So now that we've gone through the basics of a purely capacitive AC circuit, let's have a look at some examples to actually appreciate what we are doing. So we have a problem here, and the problem is asking us to determine the capacitive reactance of a capacitor of 10 microfarad when connected to a circuit of frequency A 50 Hz and B 20 kilohertz. Now this is pretty easy, pretty straightforward. So the first thing you want to do is to write down your solution, and then as always I will recommend you write all the parameters that you have and those that you don't have, so that you know where to go from. Alright, so I have over here, I've been given the capacitance of the capacitor, which is C, to be 10 microfarad. I know micro is times 10 raised to the power negative 6, so this is going to be 10 times 10 raised to the power minus 6 farad. That is for my capacitance. And then I've been told that it is connected to a 50 Hz AC circuit, so my frequency is 50 Hz. The question is saying that I should find the capacitive reactance XC. That is what I don't know. So for A, so I have XC is equal to VC over IC. But in this case, we are not given voltage, we've not been given any current, so we are not going to use this formula. We're going to use the formula 1 over 2 pi FC. So this is going to be equal to 1 over 2 pi. The frequency we've been given is 50 Hz for the first case, which is over here. And then we have our capacitor, the capacitance of the capacitor, having its capacitance to be 10 times 10 raised to the power negative 6 farad. Now if we compute these into our calculator, we are going to get 318.3 ohms as our answer for question number 1A. Now if we look at B, we can see that we've been given the frequency to be 20 kilohertz. 20 kilohertz is equal to 20 times 10 raised to the power positive 3 hertz. So that is what we are going to use for the calculation. And as the same, our capacitance is still 10 microfarad, and we are still to find the capacitive reactance. So this is also pretty easy, pretty straightforward. We know XC, or the capacitive reactance, is equal to the ratio of 1 over 2 pi FC. So we do the necessary substitutions. We're going to have 2 pi. Our frequency in this case is going to be 20 times 10 raised to the power positive 3, then multiplied by our capacitance is 10 times 10 raised to the power negative 6. So we compute these into our calculator, and when we do that, we are going to get our answer for our capacitive reactance to be 0.796 ohms as our capacitive reactance. So this is how we go around solving a problem that involves a purely capacitor, or a problem on a purely capacitive AC circuit. So let's have a look at another example. Problem number 2. We have a capacitor have a reactance of 40 ohms when operated on a 50 Hz supply. We are to determine the value of its capacitance. Alright, so let's write down our solution and let's try to understand the question. So the question is saying a capacitor has a reactance of 40 ohms. It means that the capacitive reactance of this particular circuit is 40 ohms. So we've been given XC straight ahead from the beginning of the question, so 40 ohms, and we've been told that this circuit has been operated on a 50 hertz frequency supply. So we have 50 hertz as our frequency. We are to determine the value of C, which is our capacitance. That is what we do not know, but we know that XC, which is our capacitive reactance, is equal to the ratio of 1 over 2 pi FC. Now if we cross multiply to make C the subject, we're going to have this divided by 1. So if we cross multiply, we're going to have 1 multiplied by 1 will give us 1 to be equal to XC multiplied by all of this will give us 2 pi FC multiplied by XC. So to make our capacitor, the capacitance, the subject, we divide both sides by 2 pi F multiplied by XC to leave this guy alone, and then we have 2 pi F multiplied by XC. So if we cancel everything here, we're going to have just the capacitance C to be equal to 1 over 2 pi F XC. Now that we've made the capacitance the subject, let's go ahead and do the substitutions and get our value. So our C is going to be equal to 1 over 2 pi. Our frequency over here is 50, and then our capacitive reactance is 40 ohms. Now if we punch these on our calculator, it is going to give us 0.00007958. okay, so this can also be written as 79.58 microfarad. So this is going to be the capacitance of the capacitor present in this particular AC circuit. Now let's have a look at one final example and then we end today's tutorial. So the last question or the last problem on this particular tutorial, we are to calculate the current taken by a 23 microfarad capacitor when connected to a 240 volt supply and then 50 hertz supply. So this is pretty easy, pretty straightforward. So let's write down our solution. So we are to calculate the current. So we don't know the current IC, we do not know. We've been given the capacitance of the capacitor. So we have C is equal to 23 times 10 raised to the power minus 6 farad, and then we've been given voltage to be 240 volts, and then we've been given frequency to be 50 hertz supply. Very good. Now remember, I said at the beginning of this tutorial that capacitive reactance is equal to the ratio of the capacitive voltage to the capacitive current. Now if we want to find the capacitive current, it means IC is going to be equal to VC over XC. We just have to interchange the position of XC and then IC over here. So this is the formula that we're going to use to find our current. But before we do that, we have no idea what our capacitive reactance is. So we need to find XC first. So we know XC is equal to 1 over 2 pi FC. So that is going to give us 1 over 2 pi. The frequency over here is 50. Our C is 23 times 10 raised to the power negative 6. And so our XC, capacitive reactance, is going to give us, if we compute everything over here into our calculator, we are going to get 138.40 ohms as our capacitive reactance. Now that we have this, we can do the substitution into this formula to get our current. So our current is going to be IC is equal to our voltage, we know is 240 volts over here, on our capacitive reactance, which we just found to be 138.40. Now if we compute these into the calculator, we are going to get 1.7 1.34, okay, which you can just do to 2 decimal places to be 1.73 amperes as our current. So this is how we solve some basic problems involving a purely capacitive AC circuit. So thank you so much for watching, and I will see you in the next video. Bye bye. Hello and welcome to MyScience Tutorials. In today's video, we want to look at a resistor-capacitor series AC circuit, or what we simply call RNC series AC circuit. Now before we begin, if you're new to MyScience Tutorials, kindly consider subscribing and turning on the notification button so that you do not miss any of our latest tutorials on biology, chemistry, mathematics, and physics. So without further ado, let's begin. So what do we mean by a resistor capacitor in series AC circuit, or what is an RNC series AC circuit? So in this type of series AC circuit, we have our major component to be a capacitor and a resistor connected to a source of an alternating current. So if we draw the circuit diagram for this particular RNC series AC circuit, we are going to have our resistor connected to a capacitor, which is then connected to an AC source. So this is our AC source. Okay, so this is our resistor, this is our capacitor. Now the current flowing through this entire circuit is over here as I. Now there is a potential difference, or different potential difference goes across each of the various components that we have over here. That is the resistor and then the capacitor. So the potential difference across the resistor over here is what we call the resistive voltage, denoted by VR, and then the potential difference across the capacitor is what we are calling the capacitive voltage, VC, over here. Now if we do something we call phasor sum of VR and VC. If we do a phasor sum of VR and VC, we are going to get the overall voltage across this entire circuit, which we are calling the applied voltage, V. Now in this type of circuit, the current we have over here leads the applied voltage by an angle between 0 to 90 degrees. So for us to illustrate what we mean by the current leads the voltage or the applied voltage by an angle between 0 to 90 degrees, we need to look at something we call the phasor diagram. The phasor diagram. So the phasor diagram for this type of circuit is like this. So we are saying the current is leading the current is leading the voltage by an angle between 0 to 90 degrees. So we have this over here, we have our current is over here, then we have, let's say from here to here is our resistive voltage, so we have VR, and then from all the way from here down here is our capacitive voltage. Now if we extend this a little bit down over here, the distance from here to here, which is the resultant of VR and VC over here, is what we are calling our applied voltage, or V. Alright, so the angle now between the the current through the entire circuit over here and the applied voltage is what we are calling the phasor angle, or the phase angle. So this angle can range between 0 degrees to 90 degrees, as you can see in this diagram over here. So from the phasor diagram we have over here, we can deduce two types of triangles over here. We have one we call the voltage triangle, and we have the second one we call the impedance triangle. So let's look at the voltage triangle and then the parameters that we can obtain from the voltage triangle. So we have the voltage triangle. The voltage triangle is just, we are taking the VR and then the VC over here, and then the resultant over here, which we are calling the applied voltage. So it looks something like this. Okay, so over here we have our VR, which is our resistive voltage, which is given to us by IR, current multiplied by resistance. Then we have our VC over here, which is I multiplied by capacitive reactance XC. And then we have our V, which is our resultant over here, is equal to I multiplied by Z. The Z over here is what we call the impedance, which is the overall resistance to the flow of current in this entire RNC circuit. Okay, so the angle over here, as we can see from the top over here, is what we are calling the phase angle, and then over here is 90 degrees. So this is the voltage triangle. The second one is what we call the impedance triangle. Now, the impedance triangle is also the same as the voltage triangle. The only difference over here is instead of writing the respective voltages over here, we just write the respective oppositions to the flow of current. So it's going to be like this. This is 90 degrees. This is our phase angle. And over here, we are going to have our resistance, okay, which is the oppositions to the flow of current in a direct current way. Then we have our VC, opposition to the flow of current in an AC circuit containing just a capacitor, is what we are calling the capacitive reactance. So we have X over here. And then the opposition to the flow of current in this entire circuit is what I said we call the impedance. So Z over here. Okay, so let's look at some of the parameters or some of the things that we can find from this voltage triangle and the impedance triangle. Now, if you want to find the voltage over here, which is the applied voltage, we need to use the Pythagoras theorem. So using the Pythagoras theorem, we know that the resultant, which is the longest or the hypotenuse over here, the resultant square, V squared, will be equal to the adjacent and then the opposite square, the sum of those. So we have VR squared plus VC squared. So if we make V the subject, we are going to get the root of VR squared plus VC squared. So this is what we are calling the phasor sum of VR and VC, because we can see we are adding VR and VC, either this or this. So the phasor sum of VR and VC is what we are calling the applied voltage, and this is how we do the phasor sum. So this is how we find the applied voltage in this given scenario. Now, for us to find the angle over here, which is the phasor angle that we have over here, we can see that from this particular triangle, we will be given resistance, or the VR, we will be given VC, but we do not know the V, which is the applied potential difference or applied voltage. That is how come we found that first. So for us to find this angle, we have over here, this is the opposite side, and then this is the adjacent. So the trigonometric ratio that gives us opposite and adjacent is 2r, which is tan. So we have over here tan the phase angle will be equal to the opposite, which is VC over here, will be at the top. So we have VC over VR over here will not be at the base, VR over here. So this is how we find the phase angle if we use the voltage triangle. So this equation, equation number 1, this equation, equation number 2, they are very, very important equations that we need to use and we need to keep in mind. Now, if we look at the impedance triangle over here, let me use another color. If we look at the impedance triangle we have over here, if we want to find the impedance over here, it's going to be the same as how we find the applied voltage over here. Because this is the hypotenuse, we're going to have Z squared will be equal to R squared over here plus XC squared. So the impedance Z will now be equal to the root of the resistance squared plus XC squared over here. So this is equation 3, another very, very important equation that we need to keep in mind when we are solving problems related to R and C series AC circuit. From this triangle as well, the impedance triangle, we can find the phasor angle over here. So again, this is our opposite, this is our adjacent. So it means that if we want to find the phase angle over here, it is going to be tan alpha, or the tan phasor angle, is equal to XC, which is the opposite or the capacitive reactance, over R, which is the resistance of the resistor in the circuit. So this is equation number 4. So equation number 1, that is how to find the applied potential difference or the applied voltage. Equation number 2, how to find the phase angle when you have the when you have the capacitive voltage and then the resistive voltage. Equation number 3, how to find the impedance or the overall opposition to the flow of current in this circuit. And then equation number 4, which is something similar to equation number 2, that is how to find the phase angle when you have the capacitive reactance and then the resistance of the resistor in your equation. So these 4 equations are very, very important, and let's keep them in mind. So now that we've gone through the basics of R and C series AC circuit, and we've looked at all the important equations that we need to note, let's proceed to have a look at some few examples to really appreciate what we are doing over here. So the first question we want to try our hands on is problem number 1. We have a resistor of 25 ohms is connected in series, this is very important, in series, not in parallel, in series, with a capacitor of 45 microfarad. We are to calculate A, the impedance, and B, the current taken from a 240 volt 50 hertz supply. Find also the phase angle between the supply voltage and the current. This is very easy and very straightforward question to do. So let's write down our solution. Now, the first thing I want to do is to write all the parameters that I have and those that I don't have. That way I know where to start and where to end. So I have a resistor of resistance 25 ohms. So R is equal to 25 ohms. And I was told it is connected in series to a capacitor which has a capacitance of 45 microfarad. So I was told to calculate the impedance, the current, if I have a voltage or the applied voltage of 240 volts and then a frequency of 50 hertz. Right, this is beautiful. Let me try and draw the circuit diagram for this particular question. So let's draw the circuit diagram so that you can understand what is going on. The circuit diagram. Okay, so the circuit diagram is going to look like this. I have my resistor over here, and then I have my capacitor connected to it in series, and then I have my AC source over here. Okay, so my current is over here, I don't know. My applied voltage is 240 volts and the frequency of 50 hertz. My capacitance C is 45 microfarad. My resistor has a resistance of 25 ohms. Then we have our VR over here. And then we have our VC over here. Okay, so this is our circuit diagram for this particular example. So the first thing we've been asked to find is to find the impedance. So A, impedance. We know that impedance is the total opposition to the flow of current in this R and C series AC circuit. So from the previous explanation that I gave, I said the impedance is equal to the root of R squared plus XC squared. Now we have R, which is the resistance we have over here, but we don't know XC, which is the capacitive reactance. Now the capacitive reactance of a capacitor is given by the formula 1 over 2 pi Fc, where F is the frequency of the circuit and then C is the capacitance of the capacitor. So let's have a look at that. So this is going to be, we have 1 over 2 pi, our frequency is 50 hertz, multiplied by the capacitance of the capacitor, which is 45 microfarad. So 45 times 10 raised to the power minus 6 over here. Now if we compute everything we have over here into our calculator, 1 over 2 pi multiplied by 50 multiplied by 45 times 10 raised to the power negative 6 is going to give me 70.74 ohms as my capacitive reactance. Now that I have my capacitive reactance, I can go ahead and find my impedance. So Z, which is my impedance, is going to be the root of my resistance is 25 squared plus my capacitive reactance is 70.74. I also squared that as well. So if I compute everything over here into my calculator, 25 squared plus 70.74 squared, the root of that answer, will give me 75.03 ohms as the opposition to the flow of the current in this entire circuit, or as the impedance over here. So now that we found the impedance, let's go ahead and tackle the B aspect of this question. Let me do it at the top here. The B is saying we should find the current taken from this particular circuit. So we know that voltage is equal to current multiplied by the impedance. The applied voltage is equal to current multiplied by the impedance. So if we want to find our current, which is I, we need to divide both sides by Z, or the impedance. We are going to have voltage, applied voltage, over the impedance. That will give us our current. So therefore, our current is equal to, our applied voltage has been given to us to be 240 volts over here. We just found our impedance over here to be 75.03. So we have 75.03. If we compute 240 on 75.03, we are going to get 3.20 amperes as our current flowing through this particular circuit. Now, we've also been tasked to find the phase angle between the voltage and the current. So that is easy. Let me use that as C. So we said that tan the phase angle will be equal to VC over VR, or it's also equal to XC over R. Now, if we look at what we have over here, we know that we've not been given VC or VR. Even though we can find it, let's not do that. So we can just use XC, which is the capacitive reactance, which is what we found over here, and then the resistance of the resistor, which is given to us as 25 over here. So we have tan phase angle is equal to, our XC is 70.74 divided by 25 as the resistance for rest. So to find alpha, or the phase angle, we take the tan inverse of our ratio 70.74 all on 25. And if we do that, it is going to give us the phase angle will be equal to 70.54 degrees. So this is our phase angle. Our phase angle is 70.54. Alright, let's have a look at another example to further enhance our understanding of this R and C series AC circuit. So let's look at problem number 2. We have a capacitor C is connected in series with a 40 ohm resistor across a supply of frequency 60 Hz. A current of 3 amperes flows and the circuit impedance is 50 ohms. We are to calculate I, the value of the capacitance C, B, the supply voltage, C, the phase angle between the supply voltage and the current, and D, the potential difference across the resistor, and E, the potential difference across the capacitor. We are also to draw the phasor diagram for this particular segment. So let's go ahead and look at how to tackle this problem. So let's write down our solution. Okay, so we have a capacitor connected in series with a 40 ohm resistor. So we have our resistance is 40 ohms, and then we have our frequency to be 60 Hz. We have a current which is 3 amperes, and then the impedance of the entire circuit, we've been told is 50 ohms, which is what we have over here. Now we have to calculate the value of the capacitance C. All right, so let's look at how we find that over here. So we know, or we've been given from the question, that the impedance is equal to 50, but we know that the impedance is equal to the root of R plus XC, and we also know that XC is equal to 1 over 2 pi FC. So the C we want to find, until we get the XC, which is the capacitive reactance, we cannot find that. So this will be on hold. So let's try and find XC over here, and then we can use that to find our capacitance, which is C over here. So we've been given the impedance to be 50. So we have 50 is equal to the root of our resistance is 40. So we have 40 squared. Sorry, this is supposed to be squared plus XC squared. So this is equal to, if we get rid of the root sign, we square both sides. So this cancels the root. We have 50 squared is equal to 40 squared plus XC squared. From there, we move the 40 squared to the other side of the equal to sign. So we have 50 squared minus 40 squared is equal to XC squared over here. All right, so to find this, we take root of this. So XC is now equal to the root of 50 squared minus 40 squared. So XC, which is our capacitive reactance, is going to be equal to the root of 50 squared minus 40 squared will give us 30 ohms as our answer. So now that we have our 30 ohms, we know that XC is equal to 1 over 2 pi FC. So to find C, or if we make C the subject, we are going to have 1 over 2 pi F multiplied by XC. So from there, we can write C is equal to 1 over 2 pi. Our frequency is 60 over here, multiplied by XC, which we just found to be 30 over here. So if we compute everything over here into the calculator, we are going to get our capacitance C to be equal to 88.42 microfarad. So this is the value of our capacitance over here. Now the B is asking us to find the supply voltage. All right, so we know that V is equal to IZ. This is B. But we've been told that the current is 3 amperes, and we found our impedance, or the impedance given to us in the question, is 50 ohms. So this is pretty easy. We know V is equal to 3, which is the current, multiplied by 50, which is the impedance. So this will give us 150 volts as our answer over here. Now let's look at C, the phase angle. The phase angle, we know that tan the phase angle will be equal to XC over R. So our phase angle is the tan inverse of XC, which we found earlier on is 30 over here. So we have 30 over the resistance, which was given to us in the question, is 40. So the tan inverse of the ratio 30 is to 40 will give us an angle of 36.87 degrees. Okay, now that we are done from here, let's try and find the potential difference across the resistor, which is VR, and then the potential difference across the capacitor. So let me quickly get some space over here. Okay, now the potential difference across the resistor VR is given to us mathematically as I, which is the current, multiplied by the resistance. So our VR is equal to, our current is 3, and then our resistance is 40 over here. So if we do that, if we multiply this, we are going to get 120 volts as our VR, or the potential difference across the resistor. Now let's go ahead and look at the potential difference across the capacitor VC. VC is given as I multiplied by XC. So it means VC is equal to 3 which is our current, multiplied by our XC, which we found earlier on, was 30. So it means VC is equal to 3 multiplied by 30 will give us 90 volts as our capacitive voltage. Now, we found earlier that our applied voltage, or V, for the entire circuit was 150 volts, which we found earlier. So if that is the case, let's try and see whether the phasor sum of VR and then VC will give us 150. We know that V is equal to the root of VR squared plus VC squared. So the root of VR is 120, so we have 120 squared plus 90 squared. Let's compute these into our calculators and see whether we get V to be equal to 150 volts. If we get 150, it means that this is correct and this is also correct. And if we compute this into our calculator, we are going to get 150, which means our potential difference across the resistor VR and then our VC is also correct. Now this is D and this is E. Now let's look at the final one. We have to draw the phasor diagram. Okay, so the phasor diagram F looks like this. Okay, so we have our current over here, which is 3 amperes. Then we have our resistive voltage, which is 120 volts here. We have our capacitive voltage, which is 90 volts also over here. Then we extend this guy a little down here to see where it will meet with this guy, and that will give us our resultant, which we are saying is our voltage or applied voltage, which is equal to 150 volts over there. We also find the phasor angle to be equal to 36.87 degrees. Okay, so this is our phasor angle. So this is the phasor diagram for this particular example. All right, so problem number 3. For the sake of practice, kindly go ahead and try and solve problem number 3. I will give you 3 minutes for that, and once you are done, we can continue. All right, so I assume you've paused the video and you've tried your hands on problem number 3. Now let's have a look at the solution. So we have a voltage of 35 volts is applied across a CR series circuit. If the voltage across the resistor is 21 volts, find the voltage across the capacitor. All right, so we've been told that the voltage of 35 volts is applied across the CR series circuit, which means our applied voltage is equal to 35 volts. Okay, we've also been told that the voltage across the resistor VR is equal to 21 volts. So we have to find the voltage across the capacitor, which is VC. We do not know that, but we know very well that the phasor sum of VR and VC will give us our applied potential difference or applied voltage. So we know that our V is equal to the root of VR squared plus VC squared. Okay, so now that we have this and we have to find VC, let's make VC the subject. So we square both sides. So we get rid of the root here. We have V squared is equal to VR squared plus VC squared. So let's make VC the subject. So we leave it here, move the VR to the other side. We have VR squared, V squared minus VR squared is equal to VC squared. So to make VC the subject, we take the root of both sides. So the root of this side, the root of this side. So this cancels this. We have our VC to now be equal to the root of V squared minus VR squared. So we can go ahead and do the substitution. Our voltage over here is 35 squared minus our VR is 21 squared. So our VC, which is the voltage across the capacitor is equal to 35 squared minus 21 squared, and the root of that answer will give us 28 volts as the voltage across our capacitor. So thank you so much for watching. That is how we solve problems on a resistor capacitor in series in an AC circuit. So thank you so much for watching, and I will see you in the next video. Bye bye. Hello and welcome to my science tutorials. In today's video, we want to look at problems involving RC series AC circuit, or problems involving a resistor and a capacitor connected in series in an AC circuit. Before we begin, if you're new to my science tutorials, kindly consider subscribing and turning on the notification button so that you do not miss any of our latest tutorials on biology, chemistry, mathematics, and physics. So without further ado, let's begin. So in our previous tutorial, we'll look at R and C series AC circuit, where we'll look at all the important parameters, all the important formulas that we need to note and use when we are solving problems involving an R and C series AC circuit. Now in this video, we want to look at further questions to further enhance our understanding of this concept. Now if you've already watched our previous tutorial, then you are good to go. If not, I'll leave a link in the description of this video so that you can go and have access to that video. All right, so let's go ahead and look at the first problem that we have for today. So we have a resistor of 50 ohms is connected in series with a capacitor of 20 microfarad. If a supply of 200 volts 100 hertz frequency is connected across the arrangement, we have to find the impedance of the circuit, B, the current flowing through the circuit, and C, the phase angle between the voltage and the current. This is very easy. This is pretty straightforward. So let's go ahead and write down our solution. Okay, so we have a resistor that has a resistance of 50 ohms given to us in the question, and we've been told it is connected to a capacitor of capacitance 20 microfarad. We also have our applied voltage, or the root mean square voltage, to be 200 volts, and then frequency to be 100 hertz. All right, so let's go ahead and draw the circuit diagram for this particular problem. So we have a resistor here which is connected to a capacitor in series, and then they are both connected to an AC source over here. So this is the flow of current, and then we have the potential difference across the resistor is what we are calling the resistive voltage, and then the potential difference across the capacitor is what we are calling the capacitive voltage. Then we have our voltage given to us to be 200 volts with 100 hertz frequency. Then we have our capacitor having a capacitance of 20 microfarad, and then our resistor have a resistance of 50 ohms. Okay, so the first thing we want to look at is to find the impedance of the circuit. Now the impedance of an R and C series AC circuit is given to us mathematically as the root of R squared plus XC squared. So for those of you who don't know, R is the resistance of the resistor, so this is the resistance of a resistor, and then XC is what we are calling the capacitive reactance. Now this capacitive reactance is the opposition to the flow of current in a circuit that has a capacitor in it. Now for us to find Z, which is the impedance, we need to first of all find the capacitive reactance, because we do not have that given to us in the question. We have the resistance but not the capacitive reactance. We only have the capacitance of the capacitor. So we say but XC is given to us mathematically as 1 over 2 pi FC. So we have 1 over 2 pi FC. That is the formula for our capacitive reactance. So if we do the substitution, we have 2 pi. Our frequency is 100 hertz, which we can see over here. And then our capacitance of the capacitor is 20 microfarad. So we have 20 times 10 to the power negative 6. Okay, so if we compute everything here into our calculator, our capacitive reactance is going to be equal to 79.58 ohms as our answer. So now that we found that, we can go ahead and find our impedance, which is equal to the root of our resistance is 50 ohms, so we have 50 squared plus 79.58 squared. Now, if we compute everything over here into our calculator, we are going to get the value for the impedance to be 93.98 ohms as our answer for the impedance for this particular entire circuit. Now, the B aspect of the question demands that we find the current flowing through the entire circuit. Now, for this RNC series AC circuit, the voltage is equal to the current multiplied by the impedance, which we said the impedance is the opposition to the flow of current in this particular circuit. Now, we've been given the voltage to be 200 is equal to the current we do not know, but we just found our impedance to be 93.98. So if we divide that, we divide both sides by 93.98, we are going to get the value of our current I to be equal to 200 on 93.98 is going to give us 2.13 amperes as the value of our current flowing through this entire circuit over here. Okay, so the last thing we want to look at is to find the phase angle between the voltage and the current. So to find the phase angle, which is the angle between the current and the voltage, it is given to us as tan the phase angle is equal to the capacitive reactance over the resistor. So over the resistance, so we have our angle is equal to the tan inverse, let me clean that. So we have the tan inverse of our XC, which is our capacitive reactance, is what we have over here, 79.58, on our resistance is 50 ohms, so we have 50 ohms over here. Now, if we find the tan inverse of that ratio, which is 79.58 on 50, we are going to get an angle of 57.86 degrees as our answer. So this is how we solve this particular problem. Now let's have a look at another example. Problem number 2. We have an alternating voltage V, which is equal to 250 sine 800t volts, is applied across a series circuit containing 30 ohm resistor and 50 microfarad capacitor. We are to calculate A, the circuit impedance, B, the current flowing, C, the potential difference across the resistor, D, potential difference across the capacitor, and E, the phase angle between the voltage and the current. So let's go ahead and look at how we solve this particular problem. Now, solution. So we have an alternating current with voltage. The voltage has been given to us to be 250 sine 800t. Now, this voltage is given to us in a wave form. Now, when we are given the voltage in a waveform, the actual form that this waveform of a voltage is written is V is equal to V naught sine 2 pi ft over here. So if we compare this and then the original form, we can see that our V naught is equal to the 250 over here, and then our 2 pi f is equal to, because we have t here, it means the 2 pi f is equal to the 800 over here. So those are the information that we can obtain from this particular voltage given in a waveform. Now note the 250 volt over here, this is in volt, this is in radians per second. Now remember, the voltage over here, the V0, is not the voltage that we need to use in an alternating current. We need what we call the root mean square voltage, or the applied voltage, which we are going to look at how we can derive that. So for now, let's have the other parameters that we have in this question. So we have a resistor of resistance 30 ohms. So we have a resistor having 30 ohms, and then we have a capacitor with capacitance 50 microfarad. Okay, so let's go ahead and look at the first aspect of this question, I or A. We have to calculate the circuit impedance. So the impedance Z is equal to the root of R squared plus XC squared. As usual, or as we saw in the previous example, XC is equal to 1 over 2 pi FC, which is equal to 1 over our 2 pi F is 800, which we can see over here, multiplied by the C, which is the capacitance of the capacitor, that is 50 times 10 raised to the power minus 6. Okay, so if we multiply all that, we are going to get our capacitive reactance to be equal to 25 ohms over here. So now that we have that, we can go ahead and do the substitution into this formula over here. Let's say that is equation 1. So if we substitute this into equation 1, we are going to get our resistance is 30 ohms. So we have 30 squared plus 25 squared over here. So our impedance is equal to the root of 30 squared plus 25 squared is equal to 39.05 ohms. So that is the answer for our impedance for the circuit. So let's look at B, the current flowing through the circuit. Now we know that the root mean square voltage, or the applied voltage, is equal to IZ. Now we don't know current, which is what we've been asked to find. We found the impedance, which is what we have over here, but we do not know the voltage or the applied voltage that we need to use over here. We only have something we call the V0, or the peak voltage. Now to find the root mean square voltage, or this voltage over here, this voltage, okay, either this or this, is given to us as V0 multiplied by 0.707. Sorry, let me clean that and write it well. So let me clean everything here and rewrite that to be much more clearer. So we are saying our voltage is equal to 0.707 multiplied by V0. So that will be equal to 0.707 multiplied by our V0 is 250 volts. So if we multiply all that we have, we are going to get our applied voltage across this circuit to be 176.75 volts, 5 volts, as the voltage for our entire circuit. Now using that voltage, we can now find our current over here. So if we make current the subject, we are going to have our voltage over the impedance, which is equal to our voltage we found to be 176.75 divided by the impedance, which we found earlier was 39.05. So if we divide everything we have over here, we are going to get our current to be 4.53 amperes as our answer for the current. Now the C is saying we should find the potential difference across the resistor. So that is VR, potential difference across the resistor. It is given to us by or as IR, where I is our current, which we just found to be 4.53, and then R is the resistance of the resistor, which is 30 ohms over here. So we have 4.53 multiplied by 30 over here. Okay, so if we compute that into our calculator, 4.53 multiplied by 30 will give us 135.9 volts. Okay, so the D aspect of the question says we should find the potential difference across the capacitor VC. VC is equal to IXC, where the XC we found to be what? 25 ohms over here at the top. So here is also going to be 4.53 multiplied by 25. And if we multiply these two, we are going to get 113.25 volts as our capacitive voltage. Alright, so the last thing we want to look at, which is the E, is to find the phase angle between the voltage and the current. So let's do that in another color. So to find the phase angle between the voltage and the current, it is given as tan the phase angle is equal to XC over R or VC over VR. Any of this ratio can give you the answer that you want. Because we have VR, we have VC here, we can use these guys. Or because we have XC over here and then the resistance given to us, we can also use that as well. So I will be using this guy, XC over R. So my angle is now equal to the tan inverse of XC, the capacitive reactance, is 25 over the resistance of the resistor, which is 30 over here. So my angle or the phase angle is equal to the tan inverse of this ratio will give me the angle 39.81 degrees. Okay, so this is my phase angle for this particular problem. Now let's have a look at one more final example. Now quickly pause the video and attempt to solve this problem on your own, and let's see what you get as your answer. Once you are done, you can start playing this video and look at the solution that I will provide. Okay, so I believe you are now done, and so let's go ahead and look at the solution that you found for this problem. So we have solution. We have a 400 ohms resistor is connected in series with a 2358 picofarad capacitor across a 12 volt AC supply. We have to determine the supply frequency if the current flowing through the circuit is 24 milliamperes. This is very good. So let's look at the parameters that we have. We have our resistance of 400 ohms. Sorry, the unit is not here. Then we have connected to a capacitor with capacitance of 2358 picofarad. Then we have our voltage is 12 volts, and then we've been asked to find the frequency, which we do not know, but we also know that the current flowing through this entire circuit is 24 milliamperes. So that is very good news. Now for us to find the frequency, we first of all need to find what we are calling the impedance through a circuit, because we have voltage is equal to current multiplied by the impedance. Now we have voltage, we have the current, we can find the impedance. After finding the impedance, then we can go ahead to find our capacitive reactance, which will then enable us to find the frequency that we are looking for. So if we use that approach, we are going to have 12 volts over here is equal to the current is 24. So we have 24 times 10 raised to the power negative 3 multiplied by our impedance. So we divide both sides by 24 times 10 raised to the power minus 3 over here 24 times 10 to the power negative 3. So we have our impedance to be equal to 12 on 24 times 10 raised to the power negative 3 will give us 500 ohms as our impedance for this particular circuit. Now that we have the impedance, we know that impedance is equal to the root of R squared plus capacitive reactance squared. So we know that Z squared minus r squared will give us xc squared. And so the root of z squared minus r squared will give us our capacitive reactance, which is what we are looking for. So if we do the substitution, we have our impedance is 500. So we have 500 squared minus our resistance is 400. So we have 400 squared to be equal to capacitive reactance. So our capacitive reactance will now be equal to the root of 500 squared minus 400 squared will give us 300 ohms as our capacitive reactance. But also from here, we know that our capacitive reactance is equal to 1 over 2 pi fc. But we are looking for the frequency over here. So if we make the frequency the subject, we interchange the position of the frequency and then the xc over here. So we have our frequency will be equal to 1 over 2 pi c multiplied by xc. So it means our frequency is equal to 1 over 2 pi. Our capacitance is 2358. Pico is times 10 raised to the power negative 12. Then multiplied by our capacitive reactance, which is 300 over here. So using our calculator to compute this entire ratio that we have over here, we are going to get our answer to be equal to, let me write it at the top over here. So our frequency is going to be equal to 225 times 10 raised to the power 3 hertz. Okay, so which we can rewrite as 225 kilohertz as our final answer. So this is the frequency of the entire circuit. So thank you so much for watching. This is how we solve problems on RNC series AC circuit. I hope this video has been very helpful to you to really appreciate how to maneuver your way around problems that has a resistor and a capacitor connected in series with an AC source as their voltage supply. So thank you once again for watching, and I will see you in the next video. Bye bye. Hello and welcome to MyScience Tutorials. In today's video, we want to look at a resistor-inductor series AC circuit, or what we normally just call RL series AC circuit. Before we begin, if you're new to MyScience Tutorials, kindly consider subscribing and turning on that notification button so that you do not miss any of our latest tutorials on biology, chemistry, mathematics, and physics. Without further ado, let's begin. So an R and L series AC circuit, this is just the type of circuit that contains an inductor and a resistor as the main component or the major component. So if we draw the circuit diagram for this particular circuit, we have a resistor which is connected to an inductor, and then they are all connected to an AC source in this way. So the voltage across the inductor is what we call VL, which is the inductive voltage. So the inductor is L, the resistor is R. The voltage across the inductor is what we call the inductive voltage, and then the voltage across the resistor is what we call the resistive voltage. Now we have the total current passing through this entire circuit. Since they are in series, the same current pass through all of them. And then the voltage over here supplied by the source of AC is what we are calling the applied voltage. Now the applied voltage is the phasor sum of VR and VL over here. I'm going to be explaining what the phasor sum means later on in the tutorial. Now in this circuit, the current lags the applied voltage by an angle between 0 to 90 degrees. So we are saying that if we draw the phasor diagram for this particular circuit, we are going to have something that looks like this. We're going to have our resistive voltage over here. We're going to have our inductive voltage along this line. And then we're going to have our applied voltage is somewhere in between the resistive voltage, and then the inductive voltage. Now, the angle it makes with the resistive voltage or the horizontal component of this axis, that angle is what we are calling the phasor angle. So this is what we call the phasor diagram. This is the phasor diagram. And then over here, this is our applied voltage. This is our circuit diagram. Now, from this phasor diagram, if we extend this to complete the triangle that we have over here, we can make some deductions from this particular phasor diagram. So we can have something we call the voltage triangle and then the impedance triangle from this phasor diagram. So let's have a look at that. So the first one I want to look at is what we call the voltage triangle, and it looks exactly like what we have over here. We have the phasor angle over here. This is 90 degrees over here because it's a right angle triangle. And since we have the VL on the vertical axis over here, it corresponds to the length over here as well. So we have our VL over here, the inductive voltage, and then we have our resistive voltage VR on the horizontal axis, and then the applied voltage on the hypotenuse side of this. Now, the applied voltage is equal to IZ. The Z over here is what we call the impedance, which is the overall opposition to the flow of current in any AC circuit. The inductive voltage over here is the product of the current multiplied by the inductive resistance XL, and then VR, like in direct current, we know is equal to IR, which is current multiplied by the resistor. Right, so this is what we are calling the voltage triangle. Voltage triangle. Now, another triangle we can get is what we are calling the impedance triangle. So from the impedance triangle, it is still just the same, only that over here we are looking at the impedance or the opposition to the flow of current. So we know that over here is supposed to be the applied voltage, but instead of that, we're going to put Z, which is the impedance of the entire circuit. Over here, we know we are supposed to, on this axis, the vertical axis over here, we are supposed to put the inductive voltage, but we're going to put the inductive reactance over here, and over here we're going to put R over here. So this is what we are calling our impedance triangle. Impedance triangle. Okay, and then our phasor angle is over here. Now, from these two angles, the voltage triangle and then the impedance triangle, we can make some calculations. So let's have a look at what we can find from these two angles. Let me use a blue color for that. So using Pythagoras theorem, from this voltage triangle, if we want to find the applied voltage, which is the hypotenuse over here, that will be equal to V squared is equal to VR squared plus VL squared. If we make V the subject, we are going to have the square root of VR squared plus VL squared. And now this is what we are calling the phasor sum. Okay, the phasor sum of the resistive voltage and then the inductive voltage to get the applied voltage. So we said that the applied voltage can be obtained by the phasor sum of the resistive voltage and the inductive voltage. And then this is what we are calling the phasor sum. Phasor sum. Either this or what I gave earlier on over here. So this is how we find the applied voltage in this particular case. Now let's get some space and look at how we find the angle or the phase angle over here. So let me quickly erase the circuit diagram over here. All right, so if we erase Now that we have this space, let's look at how we find the phasor angle over here. Now we can see that in this type of circuit, we only have our inductive voltage and then the resistive voltage. So this is the opposite side of the triangle. This is the adjacent side of the triangle. So the trigonometric ratio that will give us opposite and adjacent is what we call tan. So we have tan, the angle, the phasor angle, to be equal to the opposite, which is VL, over the adjacent, which is VR. So it means if we want to find our phasor angle, we just need to find the tan inverse of the ratio VL over VR. So this is one important equation you need to keep in mind, and then this is another very important equation you also need to keep in mind. Now, if we look at the impedance triangle, we can also do something similar to that. To find our overall impedance for the circuit, Z is going to be equal to Z squared is equal to XL squared plus R squared. Okay, this is plus. And then to make Z a subject, we're going to have square root of XL squared plus R squared. It doesn't matter which of this you bring first, whether R or XL, you're still going to get the same answer. So this is the formula that we use. Question 3, this is the formula that we use to find the impedance of the entire circuit. So the impedance is the total or the overall opposition to the flow of current in an AC circuit containing two or more components, such as maybe an inductor, resistor, or a capacitor. Now, from the impedance triangle, again, we can also find the phasor angle. So that will also give us tan theta, or tan the phasor angle, to be equal to the opposite and then the adjacent. So the opposite is the inductive reactance over the adjacent, which is the resistance over here that we have. So to find this, we just find the tan inverse of XL over R. So this is another equation that is also very, very important for us to look at. Now, one final touch to find the, let's say, the current in the entire circuit. If you are asked to find that, we know V is equal to IR, okay, from Ohm's law. Now, in an AC circuit, or in this particular example, we are looking at the applied voltage, which can be obtained by using the phasor sum of the resistive voltage and then the inductive voltage to be equal to the current, which is the same across all components. And then the opposition to the flow of current in this particular example is what we are calling the impedance, the Z over here. So it's IZ. Okay, and then we can find this Z by finding the square root of the inductive reactance squared plus the resistance squared. That is how we find the Z over here. So this is also another important formula that we'll be using along this tutorial. So equation number 1, equation number 2, or 4, 3, and 5, they are very, very important, and we are going to be using them in solving a lot of questions which will be coming very soon. All right, so now that we've covered the basics, let's look at some practical example or some problems and see how we apply these formulas or how we use them to solve questions. So problem number 1, we have in a series RL circuit, the potential difference across the resistor R is 12 volts and the potential difference across the inductor L is 5 volts. We are to find the supply voltage and the phase angle between the current and the voltage. So this is pretty easy. For us to enhance our understanding, let me draw this particular circuit. So we have a resistor R over here, and then we have an inductor L over here, and then this is connected to an AC source that has a voltage, applied voltage, this has a current. And then we are saying that the voltage across the resistor is 12 volts. So over here, VR is equal to 12 volts. and then the voltage across the inductor, which is VL, is equal to 5 volts. All right, so now that we have this circuit diagram, we've been asked to find the supply voltage, which is the phasor sum of these two guys over here, and also find the phasor angle. That is, so if we draw the phasor diagram, we're going to have something that looks like this. We'll have our VR over here, and then we have our VL over here, and then our V in this V will be here, and this angle is what we are supposed to find. All right, so let's have a look at how we solve this problem. So the first thing we want to do is to code the formula of how to find the applied voltage. So to do that, we know V is equal to the square root of VR squared plus VL squared. Very easy, very straightforward. So we know V is equal to the root of our VR is 12 volts. So we have 12 squared plus our VL is 5. So we have 5 squared. So this is equal to, if we compute these into our calculator, we are going to get 13 volts as the answer for our supplied voltage. Now, the second part of this question is asking us to find the phase angle between the current and the voltage. To do that, we simply said tan the phase angle is equal to VL over VR, as we saw, or as we can derive from this particular diagram over here. This is opposite over adjacent, which is VR over here. We already know what our VL is. We already know what our VR is. So our angle is equal to the tan inverse of VL from the question is 5, and then VR from the question is 12. So our angle is, if we compute the tan inverse of the ratio 5 on 12, we are going to get 22.62 degrees. So this is how we solve a question involving an R and L circuit. Let's have a look at another example. Example number 2. A coil has a resistance 4 ohms and an inductance 9.55 millihenry. We are to calculate the reactance, which is the inductive reactance, the impedance, and the current taken, from a 240 volt 50 hertz supply. We are also to determine the phase angle between the voltage and the current. All right, so this is very easy, very straightforward. Let's go ahead and write down our solution. So the first thing we want to do is to note the parameters that we have so that we know how we go around this calculation. So we've been told a coil has a resistance of 4 ohms. So our R is 4 ohms. It has an inductance L to be equal to 9.55 millihenry. So we are to calculate the impedance, the reactance, the current taken from a 240 volts. So we have our voltage to be 240 volts, applied voltage. We also have our frequency to be 50 hertz. All right. So the A aspect of this question is demanding that we find the reactance. The reactance in this case is the inductive reactance, which is XL. So XL, to find the inductive reactance of an inductor, it is given by the formula 2 pi FL. So this is equal to 2 pi. Our frequency is 50 hertz. Our L, the inductance, is 9.55 times 10 raised to the power -3. So if we compute everything over here into our calculator, we are going to get 3 ohms as our answer for the reactance. So let's go ahead and find B. The B is saying we should find the impedance. We know the impedance Z is equal to the square root of R squared plus XL squared. We just found XL to be 3, so that is a good news for us. So this is equal to our R, which is the resistance, is 4. So we have 4 squared plus our XL, which is the inductive reactance, is 3. So we have 3 squared. Now, if we compute everything over here into our calculator, we are going to get 5 ohms as the total opposition to the flow of current in this particular AC circuit. The C aspect of the question is demanding we find the current in this particular circuit. So we know voltage is equal to current multiplied by the impedance. This implies that our current is equal to the ratio of voltage to the impedance. And so this is also equal to, our current is equal to, our voltage is 240 volts, and then the impedance that we just found is 5 ohms. So our total current that passes through this particular circuit is going to be the ratio of 240 to 5, and that is going to give us 48 amperes. All right, so the final aspect of the question is asking us to find the phase angle. So this is very easy. So we know that our phase angle is tan. The phase angle is equal to either VL over VR, or we have XL over R. Now, because in this case we don't have the inductive voltage and then the resistive voltage, we are going to be using XL over R. So we know our tan, the phase angle, is XL over R, and the phase angle is tan inverse of our XL is 3 over here, our R resistance is 4 over here, and so our phase angle is going to be tan inverse of 3 on 4, that is going to give us 36.87 degrees. So this is our phase angle for this particular problem. Now let's have a look at one final example. We have a coil of inductance 318.3 millihenry and negligible resistance being connected in series to a 200 ohms resistor and a 240 volt 50 hertz supply. We have to calculate the inductive reactance of the coil, the impedance of the circuit, the current in the circuit, the potential difference across each component, and then the phase angle. So this is very easy. So let's go ahead and write down our solution. Now, for the sake of those who might not be able to visualize this, let me try and draw the circuit diagram. So the circuit, we have a resistor, we have an inductor, and then we have an AC source over here. So this is how our diagram is going to be. Over here, we don't know the potential difference across each of the components. So VR and then the VL, we don't know. This is our resistor. This is our inductor L. The current I, we also don't know. But we know that the voltage is 240. And then we also have the frequency to be 50 hertz over here. We also know that the resistance is 200 ohms over here, and then the inductor is 318.3 millihenry. All right, so this is how our circuit diagram is going to look like. And then the first aspect of the question A is for us to find the inductive reactance, which is XL. And from the previous example that we did, we know that XL is equal to 2 pi FL. So with that in mind, we just write 2 pi FL, and we do the necessary substitutions. We know our frequency has been given to be 50. We have 50 here. And then our inductance is 318.3 times 10 raised to the power minus 3. Okay, so if we compute that into our calculator, we are going to get the value of XL to be equal to 100 ohms. Now, the second aspect of the question is asking us to find the impedance. We know that the impedance is equal to the square root of R squared plus XL squared. So this is equal to the square root of the resistance we know is 200 ohms, so we square that, plus we just found the inductive reactance to be 100, so we have 100 squared. Now if we compute that into our calculator, our impedance is going to have a value of 223.61 ohms. Okay, now let's continue to look at the third aspect of this question. We are to find the current flowing through this circuit. So we know that V is equal to IZ. This implies that our current is equal to the ratio of voltage to the impedance. And this is equal to, our voltage is 240 volts, so we have 240. Our resistance, which is the impedance that we just found, is 223.61. So let's divide that by, let's divide 240 by 223.61. So if we compute that into our calculator, it's going to give us a value of 1.073 amperes as our current flowing through the circuit. Now, the D aspect of the question is demanding that we find the potential difference across each component, which is VR and VL over here. So let's do that. So for VR, which is the potential difference across the resistor, is going to be IR. And we found the I, which is the current, to be 1.073 multiplied by the resistance of the resistor is 200 over here. So if we do the multiplication, we are going to get, for our VR, we are going to get 214.6 volts as our answer. Now the second one is VL. So VL, which is the inductive voltage, is the product of the current and then the inductive reactance. Just as before, our current is still 1.073 multiplied by our inductive reactance we saw earlier on was 100 ohms that we found at the top over here. So we have 100 over here. And so if we multiply this by this, we are going to get 107.3 volt. Now here is a catch for you to verify if your answer is correct. We said that the applied voltage is the phasor sum of these two voltages, so which is VR squared plus VL squared. Now we just found out that our VR is 214, so 214.6 squared plus 107.3 squared. Compute this into your calculator and see whether you get anything close or 240. If you get 240 or 239 point maybe 8 something, then this should tell you that our calculations that we've done so far up until this point, everything is correct. So that is just a quick hack. So try it and see if the answer is correct. If it is equal to 240, it means you are right. But if it is not, then it means the calculation we've done over here is wrong. So let me know your answer in the comment section below. All right, let's proceed to find the last aspect of this question, E, which is telling us to find the phase angle. So for the phase angle, we know tan the phase angle is equal to VL over VR. We just found these two guys, so we know this is equal to the tan inverse of our VL is 107.3, our VR is 214.6. So our phase angle is equal to the tan inverse of this ratio is going to give us 26.57 degrees. All right, so this is our phase angle, this is our inductive reactance, this is our impedance, this is our current, and these are our potential difference across the various components, that is the resistor and then the inductance. So thank you so much for watching, and I will see you in the next video. Bye bye. Hello and welcome to my science tutorials. In today's video, we want to look at problems involving RL series AC circuit. Now, before we begin, if you're new to my science tutorials, kindly consider subscribing and turning on the notification button so that you do not miss any of our latest tutorials on biology, chemistry, mathematics, and physics. So without further ado, let's jump into today's video. Now, in our previous tutorial, we did look at R and L circuit where we talked about all the important formulas and all the important things we need to know about this particular R and L circuit. So over there, we talk about the circuit diagram, the phasor diagram, the voltage triangle, and the impedance triangle. If you've not watched that video, I will leave a link in the description of this video so that you can go back and watch that. Now, once you are good to go, or you already have a fair idea of what an R and L circuit is made of, you are good to go and you are good to start this tutorial. All right, so we have a question here. A coil consists of a resistance of 100 ohms and an inductance of 200 millihenry. If an alternating voltage V given by V is equal to 200 sine 500 T volts is applied across the coil, we are to calculate A, the circuit impedance, B, the current flowing through the circuit, C, the potential difference across the resistance, and D, the potential difference across the inductor, and lastly E, the phase angle between the voltage and the current. So this is very simple. So let's go ahead and look at the solution for this particular problem. Alright, so we've been told that our coil consists of resistance. So we have our R is equal to 100 ohms and L, which is our inductance, is 200 millihenry. We've been told that the voltage is given in a waveform which is equal to 200 sine 500 T, and so that is all we've been given, and we've been asked to find the impedance, the current, and all other parameters. Okay, so in an AC circuit, the voltage given in that particular wave format, or in this wave format, is not the voltage that we use. We use another voltage which we are calling the applied voltage, or the root mean square voltage. Now, from here, the general formula is given as V is equal to V naught sine 2 pi f t. So if this is our equation 1 and this is our equation 2, comparing equation 1 and equation 2, we can see that V naught is equal to the 200 over here, and also this is 200 volts, and then the 2 pi f over here is equal to the 500 we have over here. So 2 pi f is equal to the 500 we have over there. So that is in radians per second. Okay, now that we have this, to actually calculate the applied voltage in this particular circuit, which is our V that we'll be using for the calculation, this is equal to root 2 on 2 V naught, or 0.707 multiplied by V naught. This is how we find the voltage in this particular case. All right, so the first thing we've been asked to find A is the impedance of the circuit. So we know that the impedance in an R and L circuit is equal to the root of the resistance squared plus the inductive reactance squared. But if we look at the parameters that we have the resistance, we have the inductance, but we don't have the inductive reactance. So we need to find that first. So XL is equal to, from our previous tutorial, we established the fact that XL is equal to 2 pi FL, where our F is the frequency, our L is the inductance that has been given to us over here. So from here, we can do the computation and we have our frequency. So from here, we can see that the 2 pi F that we have over here has been given to us to be 500. So instead of having this, let me quickly erase that. we've been given this as a group, so let's use that for the calculation. So our 2 pi f is now 500 multiplied by the inductance of the inductor, which is 200 millihenry. Milli is times 10 raised to the power -3. Okay, so if we compute this into our calculator, we are going to get 100 ohms as our inductive reactance. So now that we have our inductive reactance, we can just do the substitution back into this formula to get our impedance. So our impedance is going to be, our resistance is 100 squared plus another 100 squared, and this is going to give us the root of 100 squared plus 100 squared is equal to 141.4 ohms. So this is the impedance of the entire circuit. Now, the B aspect of this question is asking us to find the current that is flowing through the circuit. So we know that our voltage, or the root mean square voltage, is equal to IZ. We know our Z, which is the impedance, but we don't know our voltage. But remember, I said that our voltage, which is this voltage over here, is equal to this formula, which I'm saying √2 on 2 V0, or 0.707 V0. So I'm going to use the 0.707 multiplied by the V0, which we got from this expression that has been given to us in the question. And we established the fact that the V0, comparing these two equations, is equal to 200. So this will be multiplied by 200. So if we compute that into our calculator, we are going to get 141.4 ohms as, volts as our voltage. Now that we've established that fact, we can now go ahead and make current the subject over here. So if we make current the subject, we are going to have the ratio of voltage to the impedance. Now the voltage we have is 141.4, and then the impedance is also the same thing, 141.4. So this is going to give us a current of 1 amperes. Now the next thing we want to look at is the C aspect, which is the potential difference across the resistance and then the potential difference across the inductor. So let me get some space and then we continue. All right, very good. So our C, we have to find the potential difference across the resistor. The potential difference across the resistor is denoted by VR, and then it's equal to IR, just like in Ohm's law. So this is going to be equal to, our current is 1, and then our resistance, which has been given in the question to be 100, is over here. So it means our potential difference VR is equal to 100 volts. Now let's move to D. We have to find the potential difference across the inductance. So VL. Now VL is equal to IXL, where I is the current and then XL is the opposition to the flow of current in this particular circuit when there is an inductor. So it's inductive reactance XL. So from here we know our current is 1, and then our inductance XL, inductive reactance, is also 100. So we have 100 here. So this is also going to give us 100 volts. All right, now we did some calculation over here, and then we said that our voltage, which is the applied voltage for the entire circuit, is 141. So if we do a quick cross check to see whether this is true, applied voltage is equal to the root of VR squared plus VL squared. So that V is equal to the root of 100 squared, which is VR, what we found over here, plus VL, which is also 100 squared. And so if we compute this into the calculator, we are going to get 141.4 volts, which is equal to what we found over here earlier on. All right, so let's look at the last aspect of this particular question. That is asking us to find the phase angle between the voltage and the current. Now, to find the phase angle between the current and the voltage, it is given by the formula tan the phase angle is equal to VL over VR. Now that we have this, we can make the phase angle the subject by taking the tan inverse of the ratio VL over VR. Now, the angle is now equal to the tan inverse of 100, which is the VL over here. Sorry, this is 100 volts. Okay, so this is 100 over 100, which is 1. And then the tan inverse of 1 is equal to 45 degrees. So it means the phasor angle, or the phase angle between the voltage and then the current, is at an angle 45 degrees. All right, let's have a look at another problem. We have a pure inductance of 1.273 millihenry is connected in series to a pure resistance of 30 ohms. If the frequency of the sinusoidal supply is 5 kilohertz and the potential difference across the 30 resistor is 6 volts, we are to determine the value of the supply voltage and the voltage across the 1.273 millihenry inductance. We are also to draw the phasor diagram. Okay, so this is pretty easy. Let's go ahead and jump into the solution for this particular problem. So to enhance our understanding of this question, let's draw the circuit. So we have a resistor R, and then we have an inductance connected to an AC source over here. So this is our inductance L. We are saying we have an inductance of an inductor of an inductance 1.273 millihenry. We have connected to a pure resistance of 30 ohms. So this is 30 ohms. We've been told that the frequency over here is 5 kilohertz. And we've also been told that the potential difference across the resistor, the 30 ohm resistor, is 6 volts. So it means that VR is equal to 6 volts over here. And then VL, we don't know what VL is. And so we have to calculate the applied voltage, which is the entire voltage over here, and then the voltage across this particular inductor. So this is very, very easy. Let's go ahead and look at how we do that. Now, in this AC circuit, because the components are connected in series, the same current flows through all of them. And so since we have the resistance over here, the voltage across this component, we also know that we can use these two guys to find the current, and that will be the same current for the entire circuit. So let's go ahead and do that. We know VR, which is the resistive voltage, is equal to IR. So from here, we make current the subject. We get VR over R, and that is equal to VR is 6, which is 6 over here. Then the resistance of the resistor is 30. So if we do the computation, we are going to get 0.2 amperes as the current flowing through this entire circuit. Now, the next thing we want to do is to find the supply voltage. Okay, so for us to find the supply voltage over here, know that the supply voltage is given to us as V is equal to IZ, where Z is the impedance of the entire circuit. Now, we've already found the current, but we do not know our impedance, so we need to find our impedance. But our impedance is given to us as the root of the resistance squared plus the inductive reactance squared. Here again, we realize that we do not also know our inductive reactance, so we have to find that. So our inductive reactance is given mathematically as 2 pi FL. So this is 2 pi. Our frequency we've been given to be 5 kilohertz, so we have 5 times 10 to the power 3 multiplied by our inductance, which is L, which has been given to us to be 1.273 times 10 to the power minus 3 over here. So our XL, if we compute entire of this into our calculator, we are going to get 40 ohms as our answer. So now that we have this to be 40 ohms, we can calculate our impedance. So Z is equal to the root of R is 30, so we have 30 squared plus 40 squared. So if we compute this side into our calculator and find the root, we are going to get 50 ohms as our impedance. So now that we have the impedance, we can just go and do the substitution back to equation 1 to find our supply voltage. So we know that our current is 0.2, which is what we found over here. Then our impedance is 50. So we just multiply the 2 to get our voltage. So 0.2 multiplied by 50 is going to give us 10 volts as our answer. So we have that as the supply voltage. Now let's find the voltage across the inductance that we have over here, VL. So let me do that at the top corner over here. So VL will be equal to IXL, the current multiplied by the inductive reactance. Now, we already know the current to be 0.2, and then we just found the inductive reactance along the process when we're finding the impedance. So that is 40. So we use that to multiply it. So it's 0.2 multiplied by 40, and that is going to give us 8 volts. So the voltage across this inductor is 8 volts. Now, to draw the phasor diagram, this is pretty easy. So let's go ahead and look at how we draw the phasor diagram for this problem. Okay. So the phasor diagram of an R and L series AC circuit looks something like this. And then we have the applied voltage V itself over here, and then we found out to be 10V. We have the resistive voltage VR at the base over here, that was found to be 6 volts, and then we also found our VL to be 8 volts, that is also at the top over here. Now at the bottom over here as well, current is also flowing in the direction of the resistive voltage, so we have current over here to be equal to 0.2 amperes. So we can just extend these guys to meet this guy over here, and then this angle becomes our phase angle. So this diagram is what we are calling the phasor diagram. So this is our phasor diagram for this particular problem. Now let's have a look at one more final example. So problem number 3. A coil of inductance 159.2 millihenry and resistance 20 ohms is connected in series with a 60 ohm resistor to a 240 volt 50 hertz supply. We are to determine A, the impedance of the circuit, B, the current in the circuit, C, the circuit phase angle, D, the potential difference across the 60 ohm resistor, and E, the potential difference across the coil. So this is a very interesting question. So let's go ahead and write down our solution. Now for us to understand this particular question, let's have a look at the parameters that we have. So we've been told a coil has an inductance. So we have a coil, okay, that has an inductance L to be equal to 159.2 millihenry, and the same coil has some internal resistance or a resistance of 20 ohms, and then the circuit itself has, the coil is connected to a resistor, okay, an external resistor, which has 60 ohms, and then we have a voltage of 240 volts, 50 hertz supply. All right, so if we do this combination, our circuit diagram is going to look something like this. So we have a resistor and an inductor connected to another resistor, and then connected to an AC source. So the AC source has the voltage 240 volts and then 50 hertz supply. We have our current, which we do not know, and then we have our resistance over here. So this part is the coil. So let me use these dotted lines to indicate that. So this side is the coil. So the coil is made up of the resistance, which is resistor 20 ohms, and then an inductance of 159. So we have 159.2 millihenry. Then we have an external resistor here, R, it will be equal to 60 ohms over here. So the voltage across the coil over here, this side, is what we call V coil, or the applied potential difference across the coil. And then the applied potential difference across this resistor is VR, as usual. So this is our circuit diagram. But we can simplify this entire circuit diagram to become something like this. Because this resistor and this resistor are in series, okay, and we know in series we add the resistance. So the total resistance over here is going to be 80, and then connected to an inductor, and then connected to an AC source. So over here we have our current here, we have our inductance here to be 159.2 millihenry. So we can simplify this entire circuit as something that looks like this. All right, so now that we are done drawing the circuit diagram and we've fairly understood the components that we have, let's go ahead and answer the questions that follow. So A, we are to find the impedance of the circuit. Now, to find the impedance of this circuit, we need to critically look at what we have. We have two resistors and then one inductor. Okay, so our resistance, the resistance in this entire circuit is the total 80 that we have over here. So let me make this RT. So our impedance is going to be RT squared plus XL squared. So the RT is what I'm saying, that is the sum of 60 ohms over here and then the 20 ohms over here. So this is going to give us 80 ohms. Now our XL, which is the inductive reactance, is giving us 2 pi FL, and this is equal to 2 pi multiplied by the frequency 50, then multiplied by 159.2 times 10 raised to the power minus 3 Henry. So our inductive reactance, if we multiply everything over here, we are going to get 50 ohms. So now that we have this and then the total resistance, we can find the impedance for the entire circuit. So the impedance is going to be 80 squared plus 50 squared. So the root of all that we have over here is going to give us 94.34 ohms as our impedance. So now that we have the impedance, let's go ahead and find the current. So the B is saying we should find the current. So B, let me do it over here. We know voltage is equal to IZ. And so our current is equal to voltage over impedance. We know our voltage is 240, and then our impedance we just found to be 94.34. So if we compute everything over here into the calculator, we are going to get our current to be equal to 2.544 amperes. All right, so now that we've found our current, we found our impedance, let's go ahead and solve the rest of the questions. So let me get some space over here. All right, so let's look at the C aspect of this question. So the C is asking us to find the circuit phase angle. So to find the phase angle, we have tan. The phase angle is equal to, now because we've not found the voltage of the coil and then the voltage of the resistance, we can use that because ideally this is supposed to be equal to V coil over VR. But because we do not have that, we are going to use XL over R. Okay, so the tan phase angle is equal to the XL, which is what we found earlier on the inductive reactance, which we said we found out to be 50. So we have 50 over the resistance over here is going to be the total resistance. So from here is 80. So this means our phasor angle or the phase angle is equal to the tan inverse of the ratio 50 to 80 or 5 on 8. So our phase angle is equal to the tan inverse of this ratio is going to give us 32 degrees. All right, so now that we found the phase angle, let's go ahead and tackle the D aspect of this question. The D is asking us to find the potential difference across the 60 ohms resistor. So that is very easy. So VR over here is equal to IR. And then we already found our current, which I just erased previously. So we found that to be 2.544 multiplied by the resistance of the resistor over here, which is 60. And so that is going to give me 152.6 volts. All right, so let's look at E. The E is in the potential difference across the coil, V coil over here. Now, the V coil is going to be equal to the current multiplied by the impedance of the coil, V coil. Because the coil is not only having an inductor, it also has a resistor over here. So let me get some space and then we continue. So let me clean this over here. Okay, so how do we find the Z coil? So the Z coil, which is the impedance of the coil, is equal to the root of the resistance of the coil and then the capacitive inductance of the coil. Now, the capacitive inductance of the coil is equal to 2 pi. The frequency is 50 multiplied by the inductance, which is 159 over here. So we have 159.2 millihenry. So XL, if we multiply everything that we have over here, we are going to get 50 ohms as our answer. So now that we've been able to find this, we can do the substitution to find the impedance of the coil. So the impedance of the coil is equal to the root of our R is 20, so we have 20 squared plus we just found our XL to be 50, so we have 50 squared. So if we compute these into the calculator, the impedance of the coil, which is Z coil, is going to be equal to 53.85 ohms. So now that we found that, we can find the V coil very easily. We already found our current to be 2.544 multiplied by the impedance of the coil, which we just found will be this guy. We multiply that with it, so it's going to be 53.85. So if you multiply 2.544 by 53.85, we are going to get 137 volts as the voltage or the potential difference across the coil. So thank you so much for watching. This is how we solve some further problems on an R and L series AC circuit. So thank you once again for watching, and I will see you in the next video. Bye bye.
Hello and welcome to MyScience Tutorials. In today's video, we want to look at resistor, capacitor, inductor in series AC circuit, or what we simply call RLC series AC circuit. Now before we begin, if you're new to my science tutorial, kindly consider subscribing and turning on that notification button so that you do not miss any of our latest tutorials on biology, chemistry, mathematics, and physics. So without further ado, let's begin today's video. So we want to look at what is an RLC series AC circuit. So the RLC simply means resistor, inductor, and a capacitor which are connected in series. So let's look at the diagram or the or the circuit diagram for an RLC series AC circuit. So we have a resistor R connected in series to an inductor which we are representing by L, and then connected to a capacitor, and then all are connected to an AC source within the circuit. We have our current flowing in this direction, and across the resistor we have something we call the resistive voltage. Then across the inductor we have the inductive voltage VL, and then across the capacitor we have the capacitive voltage. Now the overall sum of this VR, VL, and VC gives us what we call the applied voltage of the circuit, which is V over here, and that is the phasor sum, the word phasor sum of our resistive voltage, our inductive voltage, and our capacitive voltage. Now what do we mean by phasor sum? We are going to be talking about that in a very few moments. But if we look at this diagram, or in an RLC series circuit, the VL and then the VC, okay, the inductive voltage and then the capacitive voltage are anti-phase, or they are in anti-phase manner, which is something that we can see from their resistance, okay, which is the opposition to the flow of current. We can see that in their resistance they are anti-phase, and they are displaced by an angle 180 degrees in their phasor diagram. So what do we mean by this? Now in an RLC series circuit there are three possible phasor diagrams. We have three possible phasor diagram for this type of circuit, depending on the XL and then the XC value. Now what is XL, what is XC? Now XL stands for the inductive reactance. Inductive reactance is the opposition to the flow of current that the inductor found in the circuit offers to the flow of current. So the opposition to the flow of current by the inductor is what we are calling the inductive reactance. The XC is what we are calling the capacitive reactance. And as usual, the opposition to the flow of current by the resistor is what we are calling the resistance, which is still R. So this is just our resistance. Now I'm saying that because VL and VC are anti-phase, the phasor diagram that we will have, there are three, depending on either the value of this guy or this guy. So let's look at case 1. So we want to look at the first case when the inductive reactance is greater than the capacitive reactance. But for those of you who don't know, for inductive reactance it is given mathematically as 2 pi FL, where F is the frequency in the circuit, and the L is the inductance of the inductor that we have over here in the diagram. And then for the capacitive reactance it is 1 over 2 pi FC, where F is the frequency and C is the capacitance of the capacitor that we have over here. Now you can see that the formula is, even this one is straight or is linear, this one is anti or inversely proportional. So you can see the reason why we are saying they are anti-phase in the first case. So in the case where the inductive reactance is greater than the capacitive reactance, what is the phasor diagram for this particular case? So the phasor diagram, we have a straight line no, sorry about my crooked line. Then we have our current in this direction. Now, because our resistance does not play a role in determining where the how the phasor diagram looks, it also lies in the direction of the current. So we have our VR over here, our VR, which is equal to IR by Ohm's law. And then at the top over here, we have our VL, which is our inductive voltage, which is equal to the current multiplied by the the inductive reactance. And then we have our VC over here, which is equal to current multiplied by the capacitive reactance. Now, because our XL is greater than XC, it means that the resultant of this particular guys VL and VC, because this VL is greater than VC, okay, so we'll have the resultant somewhere lying in the positive Y direction. So this guy over here will be the difference between our VL minus VC. This is their resultant. This is the lane or the resultant. This is where it's going to lie in this case, in this particular case. So if we stretch this guy along this guy across with the resistive voltage that we have over here, we're going to have our resultant voltage in this direction. So this is our V, which is the resultant voltage or the applied voltage that we have over here, which is equal to current multiplied by impedance in this way. And then the angle over here is what we are calling our phase angle in this particular case. So this is going to be our phasor diagram. Our phasor diagram for this particular case. Now, what can we obtain from this phasor diagram that we just drew? Now, if you can see, we can see some triangle over here. So let me redraw that. So we can see a triangle that looks like this. Then we have an angle over here. Now we have here VL minus VC, okay, which is the height over here, which is the same thing that's going to be over here. So here, the end over here, I'm going to have VL minus VC. Then at the top over here, which is the resultant, I'm just going to have my V, okay, which is the resultant. And then over here on the bottom, I'm going to have VR over here. Now, what if I want to get this is what we call the voltage diagram. So one of the things we can get is the voltage diagram. Now, from the voltage diagram, if we want to find the V over here, we use Pythagoras theorem, which means V squared over here will be equal to VR squared plus into bracket VL minus VC squared. Okay, this is how it's going to be. So it means our voltage or applied voltage will be equal to the root of VR squared plus into bracket VL minus VC squared. So this is the first thing we're going to get from this particular phasor diagram. So it means that in case we have the resistive voltage, the inductive voltage, and then the capacitive voltage, we can get or we can calculate the applied voltage of the circuit by using this particular formula. That is the first thing we can obtain from this triangle that we have. Now, the second thing we can obtain is the impedance, which is what we call, the opposition to the flow of current of the entire circuit in this particular case. So let's look at that one. Now, because the circuit is in series, the same current flows through them. And so if we have the same current flowing through, it means that we can ignore the current and then just use their resistance over here. So if I have the bottom over here, I'm supposed to have VR at the bottom over here, but I'm just going to have R over here since the current is constant for all this, or the current is flowing through. It is the same current flowing through all of them. So I'm going to have my resistance here over here. Then at the top over here, I'm going to have my impedance Z, which is from here, this guy. And then over here on the vertical axis over here, I'm going to have, instead of having VL minus VC, I'm going to have the XL minus XC, the inductive reactance minus the capacitive reactance. So this is what we call the impedance triangle. When we don't have their voltages but we have their resistance or their opposition to the flow of current, we call it the impedance triangle. So just like the impedance triangle, what can we obtain from the impedance triangle? We can obtain the formula for calculating the impedance or the total opposition to the flow of current by this particular circuit or network that we have over here. So that will be equal to, still using Pythagoras theorem, it means Z squared will be equal to R squared plus XL minus XC squared. And so if we want to get just Z, we're going to have impedance is equal to the root of R squared plus XL minus XC squared. So this is the impedance, or this is the formula for calculating the impedance for this particular circuit, in case we have the inductive reactance being greater than the capacitive reactance. Now there's one thing I need you to know, is that the applied voltage over here, V, is equal to the current in the circuit, I, multiplied by the impedance of the entire circuit, which is what we said we use this formula to find for the first case. All right, so what if we have the second case? Let's look at the second case when we have the capacitive reactance greater than the inductive reactance. Let's look at how the phasor diagram will look like. Now when we have XC being greater than XL, okay, we still have our phasor diagram looking like this. We still have our VL here, which is equal to IXL. We still have our VC here, which is equal to IXC. Then we still have our current in this direction. Then we still have our resistance also in this particular direction. Now in this case, because our XC, which is the capacitive reactance, is greater than the inductive reactance, it means that the resultant of these two guys will lie in the negative direction over here. So it's going to be something like this. Okay, so if we trace that with respect to the resistance over here, we're going to have something that looks like this. The resultant is going to be in this direction, so this guy is also coming to meet it over here, and then we have something that looks like this. Obviously this has to be longer than the resultant over here. So up to this point, okay, that is going to be XC minus XL, or you can say VC minus VL. That is, if you're using the reactance, you use the reactance. If you're using the voltage, you use the voltage. But for the phasor diagram, it's preferred if you use the voltage. So we are using voltage over here. Now this is how your phasor diagram is going to look like. So your phasor angle is somewhere over here. Now it means from here, the triangle we are going to get this time around is going to be inverted. It's going to be the opposite of what we had in the first case. So it's going to be like this. Then we have our phasor angle over here, and this side we're going to be VC minus VL. Okay, we're going to have our resistance over here, which is still over here, or VR. Sorry, this is supposed to be VR. We're going to have our VR in this direction, and then this is the resultant, which is going to be our V, our voltage that we want to find. The same way, this is for the voltage triangle. Voltage triangle. The same way, if we draw the impedance triangle, it's going to be the same thing. Okay, we have our phasor angle over here. Here is going to be XC minus XL. Then here is going to be our just the resistance, and here is going to be our impedance over here. So this is going to be our impedance triangle. Now from the voltage triangle, just like usual, we're going to have our V squared will be equal to, it doesn't matter, we're going to have our VR squared plus into bracket VC minus VL squared. So it means our V, or the applied voltage, is equal to VR squared plus VC minus VL squared. For the impedance, we're going to have our impedance to be equal to the root of, let me just skip one step, it's going to be the root of r squared plus xc minus xl squared. Okay, that is because we're going to have this guy squared, and then this guy, the z will also be squared. So if we take or we get rid of the square sign, we're going to have the root sign introduced on the right hand side. So this is going to be our impedance, or the formula for calculating the impedance if we have xc greater than xl. Now if you compare this to the first one that we had, which was equal to the root of r squared plus xl minus xc squared, this is for the first case, case 1, you realize that whether you have the inductive reactance first or the capacitive reactance first, because we are going to square the answer, it doesn't really matter which of the case it is, you're still going to get your answer. Your impedance is going to be the same for these particular two formulas, this guy and this guy, because we are having subtraction here and we are squaring it. So whether you subtract any of them first and you have a negative or a positive answer, you're still going to get your impedance right. But if the question demands that you draw the phasor diagram and you don't know which of these guys is greater than the other, whether the xc is greater than xl, you are not able to distinguish whether this particular triangle will lie in the negative direction or will lie in the positive or at the top over here, as we saw in this case. You don't know whether it's going to be like this or it's going to be like this. So you need to know which of these guys is greater, so that in case you've been asked to find or to draw the phasor diagram, you can be able to draw it easily. Now the third case, okay, case 3 is when we have our xc being equal to xl. Okay, when we have that particular case, it means that our phasor diagram is going to look something like this. We have our VL over here, we have our VC over here, then we have our current here, we have our VR lying in this particular direction. Now because this guy is equal to this guy, it means the resultant, which is V, will also lie in this particular direction. So our applied voltage will lie in the direction of VR. So our VR, okay, or the resistive voltage, will be equal to the voltage of the entire particular circuit. So if you look at what we have in the first case, if you look at this entire circuit, if this guy, the XL over here, is equal to the XC over here, it means that the voltage across the resistor is considered as the entire voltage for the entire circuit. That is what we are going to have. So with this explanation, we can go ahead and look at some questions on this particular diagram. Now before I go, I need to tell you how to find the phasor angle. That is very, very important. So how do you find the phasor angle? Now in the first case, let me go up. In the first case, for this particular guy, you want to find the phasor angle is going to be tan. The phasor angle is equal to, now this is tan, means TOA, TOA, opposite and adjacent. So this is our opposite. Our opposite is going to be XL minus XC over our adjacent is the bottom over here, so it's going to be R. So if you take the tan inverse of this particular ratio, you get the phasor angle over here. Now for the second case, which is this case, our phasor angle, still over here using the impedance triangle, is going to be tan the phasor angle to be equal to this guy. Okay, so we're going to have XC minus XL all over R. So this is the formula. Now you realize that because for finding the phasor angle, this is not squared, it is very important to know the order in which we have the XC or the XL. So whether the XC is greater or the XL is greater is very, very important, because that might give you positive or negative answer, and that might affect your phase angle. So it's very, very important to know whether your capacitive reactance or your inductive reactance is bigger than the other. So with that basic explanation, let's have a look at an example to further understand how to apply these formulas in solving a practical example. So the first question we want to look at, problem number 1, is a coil of resistance 5 ohms and inductance 120 millihenry in series with a 100 microfarad capacitor is connected to a 300 volt 50 hertz supply. We are to calculate A, the current flowing through the entire circuit, B, the phase difference between the voltage, the supply voltage, and the current, okay, the phase difference between them, or the phasor angle. Then C, we look at the voltage across the coil, and then the D, we look at the voltage across the capacitor. So this is a very good example which will enable us to apply all that we've all the explanation that I've given earlier on. It will really let us apply all those things. So let's look at solution. So the first thing we want to do is to draw the circuit diagram for this particular problem so that we know our left from our right. So how is the circuit diagram going to look like? So we said we have a coil of resistance and inductance. So we have a coil, but it has resistance and an inductor. So we're going to draw something like this. So we have our resistor over here. So R is equal to 5 ohms. And then we have an inductance, which is L is equal to 120 millihenry, connected to a capacitor C, which is equal to 100 microfarad. And then we have our AC source over here. Then we have our voltage over here. Then we're told that we have a 300 volts and then 50 hertz supply of AC. That is very good. So the resistor and then the inductor are both obtained from the coil. So these guys over here, these two guys, the voltage across them is what we are going to be calling V coil. So this is V coil, that is the voltage across the coil. And then from here to here, sorry, let me clean this guy. Okay, so the voltage across the capacitor is still our capacitive voltage. So this is how the circuit diagram is going to look for this particular problem. Then again, note that the coil or the V coil has the resistance and then the inductor in it as one. Now the first aspect of the question is demanding that we find the current flowing through this particular circuit. Now to find the current, we know that from Ohm's law, voltage is equal to current multiplied by the resistance in the particular circuit. So in this case, it's going to be our impedance. Okay, so we have our voltage, we don't know the current, and then we can find the impedance. So what we need to do, the first thing we need to do in this case is to find the impedance. So the impedance will be equal to the root of, we saw earlier that is going to be root of R squared plus, depending on whether XC or XL is greater, that will tell us what the formula is going to be from here. So let's go ahead and calculate our capacitive reactance, which is XC, and then our inductive reactance, which is XL, to find which of them will give us will be bigger than the other. So our capacitive reactance is 1 over 2 pi FC, 2 pi FC. So it is equal to 1 over 2 pi. Our frequency is 50 hertz, so we have 50 multiplied by our capacitor. The capacitance of the capacitor is 100 microfarad, so we have 100 times 10 raised to the power negative 6 over here. So if we compute this guy into our calculator, our XC or our capacitive reactance is going to be equal to 31.83 ohms. Alright, our inductive reactance is mathematically given as 2 pi FL. So this is equal to 2 pi. Our frequency is still 50. Our inductance is 120 millihenry, so times 10 raised to the power minus 3. If I multiply everything over here, I'm going to get 37.70 ohms as my answer. So it means that XL is greater than XC. So my formula now for the impedance will be equal to the root of R squared plus into bracket XL minus XC all squared over here. So my impedance now is equal to the resistance that I have is 5, so I'm going to have 5 squared plus the capacitive reactance minus the inductive reactance. So it's going to be 37.70 minus 31.83 all squared. So my impedance Z is equal to, now if I compute everything here into my calculator, I'm going to get a resistance or the impedance of 7.71 ohms. So this is going to be my impedance, or the overall opposition to the flow of current offered by all these components in this particular AC circuit. Now that I have this, I know that my voltage is equal to 300 volts, and so I can go ahead and say my voltage is equal to IZ. Therefore my current is equal to the ratio of voltage on the impedance that I have, and that is going to be equal to 300 for the voltage on 7.71. and if I compute this into my calculator, I'm going to get 38.91 amperes as my current. So the current flowing through this entire circuit is 38.91. That is how we apply all that we've learned to find the current in this particular case. So let's look at the second answer. The second one is saying we should find the phase angle for our problem. So we have to find the phase difference between the supply voltage and the current. So this is very easy. Let's go ahead and look at that. So to find the phase angle, it is equal to tan theta is equal to, now if we go back, we realize that these, in this case, we established the fact that our XL is greater than our XC. So let me go back. So this is going to be our XL first. We're going to have our XL at the top minus XC divided by our resistance. This is how we're going to write our phase angle formula. So our phase angle, okay, let me use this sign. Our phase angle is equal to the tan inverse of our XL. We established the fact that our XL is equal to 37.70 minus, here is 31.83, all on the resistance, in this case is 5. So our angle is equal to, if you do the subtraction over here, you're going to get, this is still going to be tan inverse, you're going to get at the top over here 5.87 divided by 5, and then the tan inverse of this ratio is going to give you 49.58 degrees. So this is our phase angle for our example number 1. Now the C aspect of the question is saying we should find the voltage across the core, and then the voltage across the capacitor. The voltage across the core and then the voltage across the capacitor. Now if you look at this variable, we realize that the coil alone has the resistance and then the inductor all embedded in one. So we need to find the overall resistance to the flow of current in that particular coil. Then we can find the voltage across it. Because we already have the current flowing through, we need to find the overall resistance. When we combine resistor and then an inductor, we need to find overall resistance before we can go ahead and find our voltage. So in doing so, it means that this is the C aspect of the question. It means that to find our current, we know that voltage is equal to current multiplied by the impedance, but this time around it is the impedance of the coil. Okay, so if you make current the subject, we're going to have our voltage over the impedance of the coil. Now the impedance of the coil is equal to, now when you have an inductor and then a resistor in series, the impedance is equal to the resistance squared x r squared plus xl squared. So this is the formula that we use to find the impedance of the coil. Okay, so it means, I'll roll this line here, the impedance of the coil will be equal to the root of r is 5, so we're going to have 5 squared plus xl is 37.70 squared over here. So the impedance of the coil, or the overall opposition to the flow of current in the coil, is equal to 38.03 ohms. So this is the impedance of the coil. So now that we have the impedance of the coil, we can go ahead and find the voltage in the coil. So sorry, this, we were to find the voltage, not the current. So we already know that our current, which we found earlier on, we found out that our current, from the first instance, we found that our current is 38.91. So our current is 38.91. Okay, so it means that our voltage is equal to I multiplied by the impedance of the coil, and that is equal to, we have the current is 38.91 multiplied by the impedance of the coil is 38.03. And then if we multiply these two guys, we are going to get our voltage, or the voltage of the coil to be precise, will be equal to 1479.75 volts. And then you can round it, round it to the nearest whole number. It will be 1480 volts. So this is the voltage of the coil. Now what is the voltage of the capacitor? So the voltage of the capacitor, VC, will be equal to the current multiplied by the capacitive reactance. We already found the capacitive reactance, so that is going to be easy. Our current is 38.91 multiplied by XC is 31.83. We found that earlier. So our VC, the voltage, or the capacitive voltage, will be equal to 1238.51 volts. So to the nearest whole number will be 1239 volts. So this is the voltage for the capacitor, or the voltage across the capacitor. Now, how are we going to draw the phasor angle? Assuming we were told to draw the phasor diagram, how are we going to draw this? So the phasor diagram is going to look something like this. We still have our resistor over here, and then our current will be at the top over here. So this is our VR in this direction. Now, because ideally this is how this is supposed to look like, we are supposed to have our VC at the bottom over here, which is IXC, and then we have our VL at the top over here, which will be equal to IXL. Now, because this XL, the inductor, and then the resistor are part of a coil, it means that they will not lie in their own axis vertically like this. It will be a little bit slanted to this direction. Okay, so we are not going to have XL and VR. We're not going to have them. We're just going to have VC, and then we're going to have the resultant, which is going to be V coil over here. So I can get rid of these guys that I wrote earlier. So this guy will not be here, and then this guy too will not be here. Okay, so we can draw this guy back in a straight line. Just the current will be over here. So this is going to be our V coil. Now it means that from here, okay, then our resultant is going to be in this direction, something like this. Okay, so this guy is going to come down like this to get our triangle. Our phasor angle is going to be somewhere here, very small. Okay, our resultant is going to be here, which is 300 volts. This is our V coil. Our VC over here, we already know the answer. Our current, we found the current to be 38.91 amperes. Okay, so this is how the phasor diagram is going to look like. So ideally this is supposed to be dot dot dot. This is supposed to be our VL, and then we have dot 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 on this line. This is supposed to be our VR over here. So this is the phasor diagram for the example that we are looking at. So this, for this example, this is the phasor diagram for it. All right, let's go ahead and look at another example. Problem number 2. So we have a 40 microfarad capacitor in series with a coil of resistance 8 ohms and inductance 80 Henry is connected to a 200 volt supply and then 100 hertz frequency. We have to calculate the circuit impedance, the current flowing, the phase angle, and then the voltage across the coil, as well as the voltage across the capacitor. Just a similar question to the first one that we did. So let's go ahead and look at that. So solution. Now, unlike in the first example, over here we have 40 micro Henry capacitor, microfarad capacitor. So we have a capacitor over here connected in series with a coil that has a resistor. So we have our resistor, and then we have our inductance somewhere here connected in series to an AC source. Okay, so our capacitor C is 40 microfarad, our resistor is 8 ohms, and then our inductance L is equal to 80 microhenry. So 80 microhenry. We are saying our inductor and then the resistor form the coil, so we have these guys, okay, as the coil. So the voltage across these guys will be V coil, and then the voltage across this guy will be VC, or the voltage across the capacitor over here. And then we have 200 volts, and then we have 100 hertz supply. Okay, so the first thing we need to do, okay, our current is in this direction. The first thing we're told to find is the circuit impedance. Very important, circuit impedance. So as usual, we need to find our XL and XC to know which is greater, to know how we are going to write our the impedance of the impedance formula. So XL is equal to 2 pi FL, that is equal to 2 pi 100 for the frequency, multiplied by the inductance, which is equal to 80 times 10 raised to the power minus 3. So we have 80 times 10 raised to the power minus 3. Then if you compute everything here into the calculator, our XL is 50.27 ohms. So for the capacitive reactance, we have 1 over 2 pi FC, which is equal to 1 over 2 pi. F is frequency, which is 100. And then the capacitance of the capacitor over here is 40 times 10 raised to the power negative 6. Right, if we compute everything over here into the calculator, we are going to get 39.79 ohms. So which means our XL is greater than XC. So from here, we can write that our impedance is equal to the root of R squared plus into bracket XL minus XC squared. So it means our impedance, this is A, is equal to the root of R squared is 8 squared plus into bracket XL is now 50.27 minus 39.79 all squared. And then if you compute everything in there into the calculator, you're going to get 13.18 ohms as your impedance. So this is how we calculate the impedance. So the second aspect, which is B, is saying that we should calculate the current flowing through. So this is very easy. We know that V is equal to IZ, okay, and then we know that our voltage is 200, is equal to our current, we don't know, but we already found our impedance to be 13.18. So we just divide the voltage by the current, so it becomes 200 on 13.18 to give us the value of our current. So if you do that, you're going to get 15.17 amperes as your current flowing through this particular circuit. Now the C aspect of the question is saying we should find the phase angle between the voltage and the current. So the phase angle is equal to we establish the fact that XL is greater than XC, so it's going to be like this over R. So this is going to be the phase angle is equal to the tan inverse of into bracket XL is 50.27 minus XC is 39.79 all divided by 8. Okay, so our phase angle is equal to the tan inverse of, if we do the division and everything over a subtraction at the top before we divide by 8, we're going to get 10.48 as our answer. So the tan inverse of 10.48 will give us an angle of 52.63 degrees over here. So let's look at the next thing we have to find. We have to find the voltage across the coil and then the voltage across the capacitor. This is very good. The first thing we need to do, this is the voltage across the coil, V coil, will be equal to the current multiplied by the impedance of the coil. Now we know that the coil is made up of the resistor and then the inductor, so it means the Z coil, the impedance of the coil, will be equal to the root of the resistance squared plus the inductive reactance squared. So this will be equal to, the resistance is 8, so it's going to be 8 squared, plus the inductive reactance is 50.27, so 50.27 squared. So if we compute everything here into the calculator, we are going to get, for the Z of the core, Z core, we're going to get 50.90 ohms as the overall position offered by the core. So from there, we can go ahead and find the voltage of the core. So V core is equal to our current. We found our current earlier to be 15.17, so we multiplied that by 50.90, which we obtain as Z coil over here. So our V coil is going to be 772.153 volts, which is basically equal to the nearest whole number, 772 volts as the voltage across the coil. Now from there, let's go ahead and answer the final question, which is asking that we find the voltage across the capacitor. So very good. This is E. Voltage across the capacitor is the current multiplied by the capacitive reactance. We already know our current to be 15.17, that we multiplied by our capacitive reactance, which we found in the previous example, XC, to be 39.79, so we multiply it by that, so we have 39.79 over here. So if you multiply everything, we are going to get 604 approximately volts as the voltage of our as the voltage across the capacitor. So thank you so much for watching. I hope this video was helpful, and now you are able to when you see an inductor, capacitor, and a resistor connected in series in an AC circuit, you are able to decipher your way and find the impedance of all the components, and use that together with the voltage to find the current and find the voltage across any of the components that you might see in the circuit. So thank you once again for watching, and I will see you in the next video. Bye bye.